Imagine a scenario where a cup shatters into fragments. Is it possible for those fragments to come together and reconstruct the cup as it was before? The answer is definitely no. But what is the reason behind this limitation? Why is it that once things are broken, they don't spontaneously come back together to restore their original form? The inability of broken objects to naturally reassemble is connected to the concept known as the arrow of time, specifically known as the thermodynamic arrow of time. But what exactly is time? Is time the same everywhere in the universe, or does it vary depending on where you are or who you are? Why is it impossible to go backward in time? Where does the distinction between the past and the future come from? And why do we have memories of the past but not of the future? Today, our focus will be answering all of these questions. Before I begin this video, I'd like to mention that I will be dividing the Arrow of Time video into two parts. In the first part, I'll cover the historical aspects and provide an overview of the types of arrows of time with some introductory information. However, in the second part, I'll delve into a more detailed exploration of this concept. We'll start our video by discussing how our understanding of time has evolved throughout history. In ancient civilizations like the Babylonians and Egyptians, time was often measured based on astronomical events such as the movement of celestial bodies. The division of time into days, months, and years played a crucial role in religious and agricultural practices. The ancient Greeks pondered the nature of time and its relation to the cosmos. Philosophers like Plato and Aristotle debated whether time was a continuous flow or composed of discrete moments. In the Middle Ages, advancements in technology led to the invention of mechanical clocks, which revolutionized how time was measured and regulated. This was a significant step toward the standardization of timekeeping. The scientific revolution of the 17th century brought about breakthroughs in understanding the fundamental nature of time. Isaac Newton's laws of motion and universal gravitation provided a mathematical framework for describing how time interacts with space and matter. In the 20th century, Albert Einstein's theory of relativity reshaped our understanding of time. Einstein proposed that time is not an absolute concept but is relative, meaning it can vary depending on the observer's motion and gravitational field. Today, with the aid of modern physics and technologies, scientists continue to explore the nature of time. The quest to reconcile the macroscopic world described by classical physics with the quantum realm has led to intriguing discussions about the true essence of time. Throughout history, our comprehension of time has undergone a gradual evolution. The arrow of time paradox initially emerged in the 1800s in the context of gases and other substances. This paradox highlighted a discrepancy between microscopic and macroscopic descriptions within the realms of thermodynamics and statistical physics. Time symmetry is a foundational concept in physics for both microscopic and macroscopic systems. However, intricacies like quantum decoherence in the micro realm and thermodynamic processes in the macro realm introduce complexities that affect our perception of time symmetry. The term, the arrow of time, or time's arrow, was formally introduced by British astrophysicist Arthur Eddington in the year 1927. The concept of one-way direction, or asymmetry, is an inherent aspect of time. It continues to pose an unresolved question in the realm of general physics and has led to various theories and discussions about the nature of time and its apparent irreversibility. Eddington proposed that the direction of time could be deduced by analyzing the arrangement of atoms, molecules, and objects and might be drawn using a four-dimensional relativistic representation of the world, often likened to a solid block of paper. Arthur Eddington, in his influential 1928 book, The Nature of the Physical World, played a significant role in popularizing the concept of the arrow of time. He expressed the idea in the following manner: let us draw an arrow arbitrarily. If, as we follow the arrow, we find more and more of the random element in the state of the world, then the arrow is pointing towards the future. If the random element decreases, the arrow points towards the past. This is the only distinction known to physics. This follows at once if our fundamental contention is admitted: the introduction of randomness is the only thing that cannot be undone. I shall use the phrase, time's arrow, to express this one-way property of time, which has no analog in space. Eddington then proceeds to highlight three crucial points about this arrow of time. The direction of time's arrow is keenly recognized by consciousness, making it a distinct and noticeable aspect of our perception of time. Our reasoning faculty strongly emphasizes this direction, indicating that a reversal of the arrow's direction would render the external world nonsensical. This underscores the fundamental nature of the asymmetry of time. The concept of time's arrow is predominantly observed within the realm of the organization of groups of individuals, particularly in the study of entropy. This phenomenon is most notably a result of statistical mechanics and arises from the behavior of systems. Eddington's exploration of time's arrow in The Nature of the Physical World provides insights into the unique nature of time's asymmetry and its significance in both consciousness and scientific understanding. The concept of time symmetry, or T-symmetry, can be simplified as follows. In a perfectly symmetrical time scenario, a video depicting real-life events would appear equally realistic when played forwards or backwards. For instance, gravity represents a time-reversible force. Consider the example of a ball being thrown upward, slowing down to a stop, and then descending. In this situation, if you were to watch recordings of the event, they would appear equally realistic whether played forward or backward. This situation is T-symmetrical. However, when examining the process of the ball bouncing and eventually coming to rest, it becomes evident that this process is not time-reversible. As the ball moves forward, kinetic energy is dissipated and entropy increases. Entropy, a concept closely linked to disorder, is one of the few phenomena that do not exhibit time reversibility. In the statistical framework of growing entropy, the arrow of time is associated with a decrease in free energy. Physicist Sean Carroll draws an analogy between the asymmetry of time and the asymmetry of space. While physical laws generally exhibit isotropy, uniformity, in space, there is a clear distinction between up and down near Earth due to its immense gravitational influence, which breaks the symmetry of space. Similarly, while physical laws are generally symmetric when time direction is flipped, there is an apparent differentiation between forward and backward in time near the Big Bang, especially within the initial several trillion years following it. This differentiation arises due to the unique circumstances associated with that extraordinary event, which disrupts the symmetry of time. In this perspective, all the arrows of time are a result of our relative proximity in time to the Big Bang and the special circumstances that existed then. Important to mention is that weak interactions, even though they don't individually look the same under spatial reflection or time reversal, follow a more complex symmetry that involves both of these aspects. So, that's how the concept of the arrow of time was historically introduced. In physics, time is often defined as what a clock reads. Imagine you and your friend are sitting in a park. You both have your own watches to keep track of time. In the past, people thought time was the same for everyone, like a universal clock that everyone would agree on. This was called absolute time. But then something interesting happened. Scientists discovered that the speed of light is the same for everyone, no matter how fast they're moving. This means that even if you're moving really fast, the speed of light will still appear the same to you as it does to someone who is stationary. This theory also gave rise to the famous equation E equals mc squared, which correlates energy and mass. If you're in a spaceship moving at half the speed of light and turn on a flashlight inside the spaceship, the light would still move away from you at the speed of light, not at the speed of light plus the speed of your spaceship. However, in real life, when you throw an object from a moving car, the speed of the object is the combination of your throwing speed and the speed of the car. This is because the object is already carrying the car's speed when you throw it. But when it comes to light, it's different. No matter how fast you're moving, light always travels at the same constant speed. It is also important to note that, in our current understanding of physics, it's not possible for objects with mass to reach or exceed the speed of light. This theory made us change our minds about time. Instead of one universal time, each person now has their own personal time. It's like each of you has a special watch that ticks differently. If you and your friends start running in different directions, your personal times might not match up anymore. Even though you both experience time, it's not the same for both of you because you're moving differently. When you move at a higher speed than your friend, you actually experience a slower rate of aging compared to him. This phenomenon has been demonstrated through the Haffel-Keating experiment. The provided video link in the description will give you more insight. Additionally, in environments with stronger gravitational fields, like those found around Jupiter, the Sun, and black holes, time also passes more slowly. This relationship between gravitational strength and the pace of aging is indeed linked to the concept that greater mass corresponds to a stronger gravitational field, leading to a decrease in the rate of aging. These phenomena are known as time dilation and gravitational time dilation. These phenomena were formulated by Albert Einstein and constitute the foundational principles of his theory of relativity. In a way, time has become more of a personal thing. It's not absolute anymore. The perception of time depends on two factors: velocity, which indicates how fast an object is moving, and the object's position within a gravitational field. This idea from the theory of relativity helped us understand that time is a bit different than we used to think. There's a significant challenge in the realm of science when attempting to merge gravity with quantum mechanics. This challenge led to the introduction of the concept of imaginary time. Imagine you're on a journey, but instead of moving forward in regular time like we experience every day, you're moving in something called imaginary time. In this imaginary time, moving forward and backward is just like moving forward and backward in regular space. For example, if you can go north, you can also turn around and go south. Similarly, if you can move forward in imaginary time, you can turn around and move backward. Now, when we look at real time, the time we're used to, there's a big difference between moving forward and backward. We remember the past because it's already happened, but we can't remember the future because it hasn't occurred yet. This is a puzzle. Why does time in real life have this difference between past and future? This is where things get fascinating. Imaginary time is a bit like a tool to help make sense of these complicated ideas. So, the reason we perceive such a big difference between the past and the future in our everyday experience might have to do with the way real time works compared to this imaginary time that's used in theoretical physics. The combination of gravity and quantum mechanics is a challenge to understand, but thinking about time in this unique way is one attempt to solve the puzzle. The laws of science are pretty amazing and work the same way whether we're talking about the past or the future. Imagine you have a set of rules that describe how things in the universe work. These rules don't care whether time is moving forward, like it does in our everyday experience, or backward. They're like a recipe that remains the same whether you're cooking breakfast in the morning or dinner at night. Scientists have found something interesting about these rules. There are 3 special actions that can be applied to objects and events, known as CPT symmetry. CPT stands for charge conjugation, parity transformation, and time reversal. C, P, and T. C means changing particles into their opposites, like turning regular particles into antiparticles. P means flipping things like a mirror image, so left and right swap places. T means reversing the direction of motion of everything, basically making things go backward. When scientists combine these operations C, P, and T, they find that the laws of science still make sense. This means that the rules are symmetrical, avoiding a bias towards either the past or the future. Imagine you had a twin on another planet made of antimatter, which is the opposite of normal matter. If that planet's inhabitants used these operations on themselves, their world would still follow the same laws of science. Even if everything seemed kind of flipped or reversed compared to our world, the basic rules would still apply. So, the laws of science are like a universal language that works no matter which way time is flowing or how things are oriented. If the laws of science are unchanged by the combination of operations C and P and also by the combination C, P, and T, they must also be unchanged under operation T alone. Yet there is a big difference between the forward and backward directions of real time in ordinary life. Imagine you have a cup of water sitting on a table. If it accidentally falls off the table and shatters on the floor, it's quite clear that the sequence of events is moving forward in time. If you were to film this happening and then play the film backward, you'd see something quite strange, the shattered pieces of the cup magically assembling themselves back onto the table to form a whole cup. Of course, this doesn't happen in real life. This example shows us that there's a fundamental difference between the way we experience time in our everyday lives and the way time works in the equations of science. According to the laws of science, they should work the same whether time is moving forward or backward. However, when we look around, we see that some processes in the world only seem to happen in one direction of time, the forward direction. The explanation for this comes from something called the second law of thermodynamics. This law talks about how things tend to naturally move from order to disorder over time. In other words, things become more random and chaotic as time goes on. This is often referred to as the increase of entropy. The cup falling and breaking is an example of the second law of thermodynamics. A whole cup is an ordered state, but when it breaks into pieces, it becomes a disordered state. This is also the reason why we don't see things like broken cups spontaneously assembling themselves back together in real life, because this would go against the second law of thermodynamics. It's like a rule that says things generally tend to get messier and more disordered with time. So, while the laws of science themselves don't really care whether time is moving forward or backward, the way things actually happen in the world has a lot to do with this idea of increasing disorder over time. The increase of disorder or entropy with time is one example of what is called an arrow of time, something that distinguishes the past from the future and gives a direction to time. There are different arrows of time. Thermodynamic arrow of time. This is the idea that disorder, or entropy, tends to increase with time. You can think of it like a messy room getting messier over time. This arrow of time is related to the fact that the second law of thermodynamics says that natural processes usually lead to more disorder and randomness. Psychological arrow of time. This arrow of time is about our perception of time passing. We remember the past but can't see the future. It's the reason we feel time is moving forward. Our memories and experiences are built on events that happened earlier, and this gives us a sense of the past and the present. Cosmological arrow of time. This arrow is connected to the expansion of the universe. Our universe is expanding, and this expansion points in a particular direction through time. It's like a cosmic flow that distinguishes one moment from another. Quantum arrow of time. In the realm of quantum mechanics, time's arrow is related to the concept of the arrow of amplitude. Quantum systems evolve through time according to the Schrödinger equation, which is a fundamental equation in quantum mechanics. While the Schrödinger equation is time-symmetric and doesn't inherently distinguish between the past and the future, the act of measurement collapses the quantum state to a specific outcome, introducing an arrow of time. This is linked to the idea of wave function collapse and the irreversibility of certain quantum processes. Particle physics, weak arrow of time. The weak force is one of the fundamental forces in particle physics, responsible for processes like beta decay. Certain particle interactions involving the weak force violate the conservation of parity and symmetry under time reversal. This implies that there's a preferred direction for these interactions in time, creating a weak arrow of time. This arrow is connected to the concept of CP violation, which plays a role in understanding the matter-antimatter asymmetry in the universe. Radiative arrow of time. This arrow is linked to the behavior of electromagnetic radiation, such as light. In many physical processes involving radiation, such as the emission and absorption of photons, there is a clear directionality in time. While the underlying equations governing these processes are time-symmetric, the macroscopic phenomena arising from them, like the one-way emission of light, exhibit an arrow of time due to the irreversibility of these interactions. Causal arrow of time. The causal arrow of time is fundamental to our understanding of cause and effect. Events in the past cause events in the present and future, but not the other way around. This concept is closely related to the second law of thermodynamics and the increase of entropy, as well as the concept of causality in the context of relativity. It's through the causal relationships between events that we build a coherent understanding of time progression. In the upcoming Part 2 video, we'll take a detailed look at the arrow of time.